Hello viewers, welcome to the session on quantum computing. Hope you might have watched my previous video on Introduction to Quantum Computing. In this video, we will see about the representation of qubits. Now let us understand the representation of qubits. The qubits is represented as ket psi. Here is the breakdown. The vertical bar is pronounced as ket, and we have the Greek letter psi. And the next, the angle bracket is part of ket notation, but it is not pronounced separately. So the entire symbol is pronounced as ket psi. And this is called the Dirac notation or the bracket notation. The basic qubit state could be written as ket 0 or ket 1. A superposition state can be written as ket psi is equal to alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers that represent the probability amplitudes of the qubits being in each state. The normalization condition is given as alpha square plus beta square is equal to 1, where alpha square gives the probability that you will find the qubit in the 0 state, and beta square gives the probability that you will find the qubit in the 1 state. Hence, we can say that alpha square plus beta square are the probabilities of measuring the qubits as 0 or 1. This equation means that the qubit is in the superposition of both the states with certain probabilities of being measured as 0 and 1. Now let us move on to the Bloch sphere. The Bloch sphere helps to visualize the superposition and the phase of a qubit, which are critical to quantum computing. The Bloch sphere is visual representation of the qubit state. Any qubit state can be represented as a point on the surface of the sphere. The north and the south pole represent the classical states ket 0 and ket 1, while at any point on the surface represents a superposition. The spin up is the one located at the north pole, which is ket 0, and spin down, which is located at the south pole, which is ket 1. The Bloch sphere provides a geometric way to understand quantum states. This is like pure states represented as points on the surface of the sphere. Example, ket 0, ket 1, ket plus, ket minus, etc. Whereas the mixed states is represented as points inside the sphere. And these corresponds to the probabilistic mixture of pure states. For example, the state ket psi is equal to alpha ket 0 plus beta ket 1. And this can be represented with the angles theta and phi. That is, ket psi is equal to cos theta by 2 ket 0 plus e power I phi sin theta by 2 ket 1, where theta determines the angle from the z-axis and phi determines the rotation around the z-axis. Next, we will move on to the matrix representation. That is the vector representation of the quantum state. So here the qubits can be represented using the matrix notation, which is useful for calculation and describing the quantum operation. A 1 qubit can be represented as a 2 cross 1 column vector. The basic states ket 0 and ket 1 are represented as column vector 1, 0 and 0, 1, or the row vector 1, 0 and 0, 1. Any arbitrary state can be represented as ket psi is equal to alpha beta in the column notation, and this is the row notation. And some examples of the valid quantum state vectors are represented are 1 by root 2, 1 by root 2, or 1 by root 2 minus 1 by root 2, and 1 by root 2 I divided 1 I by root 2. And ket plus and ket minus are called Hadamard bases, and these are orthogonal to each other. Ket plus is equal to 1 by root 2 ket 0 plus ket 1, and ket minus is equal to 1 by root 2 ket 0 minus ket 1. Whereas ket I is equal to 1 by root 2 ket 0 plus I ket 1, and minus 1 is equal to 1 by root 2 ket 0 minus I ket 1. Let us understand the qubits in detail. This one shows the qubits of size 1 with the two states ket 0 and ket 1. And this is how it is represented graphically. And this shows the vector representation. And the last one represents the quantum bit 0 in a probability function. And similarly, this one shows the vector representation of ket1, and this one shows the probabilistic function. And the qubit state is represented as ket psi is equal to alpha ket 0 plus beta ket 1, whereas the alpha and beta are the amplitude of ket 0 and ket 1, whereas the square of these number indicates the probability of the two states existing in ket 0 and ket 1. And we should remember that this alpha and beta are complex numbers. Next, we will move on to the quantum bits of size 2. Now, with the two bits, there are four possible states as ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. Now, this ket, the vector representation of ket 0, 0 is obtained by the tensor product of ket 0 with the ket 1. So, which is nothing but 1, 0, tensor product with 1, 0, you get the vector representation of ket 0, 0. Now this alpha, beta and gamma and delta are the amplitude of the vectors existing in the state ket 0 and ket 0, 1, ket 1, 0 and ket 1, 1 respectively. And these condition has to be met. Alpha square, beta square and gamma square plus delta square is equal to n. This is the normalization condition. Similarly, the quantum bits of size 3 is represented in the vector form, which is obtained with the tensor product of ket 0 with ket 0 with ket 0. Now coming to the difference between classical bits and the quantum bits. Classical bits can be in two distinct states as 0 and 1, whereas the quantum bits can be in the state ket 0 and ket 1. Or it also exists in the linear combination of two states. The classical bits can be measured completely, whereas the quantum bits can be measured partially with given probability. The classical bits cannot be changed by the measurement, whereas the quantum bits are changed by the measurement. The classical bits can be copied and erased, whereas the quantum bits cannot be copied and erased. Now coming to the advantages of qubits, and this adding qubits increases storage exponentially, whereas if you see the quantum computers, it doubles the power by adding one more qubit. It is, for example, if you want to double the power of digital computer with 32 bits, it has to be converted into 64 bits. Whereas to double the power of quantum computer with 32 bits, it is enough if you convert it into 33 bits. Next, if you see that quantum computer can do operations on all superposition, that is like a massively parallel computation. For example, one math operation on 2 power n numbers encoded in classical computers with n bits requires 2 power n steps or parallel processor. But the same operation on 2 power n numbers encoded by n qubits takes one step. This makes complex problems much easier to solve by the quantum computers. See you in my next video. Have a happy learning. Bye bye.